Okay. Because we want to find where this thing is concave up and concave down, and the inflection points, that's all from the second derivative. So we got to get there. So we got to derive it one time, which gives us low d high, which will be 2x, minus high d low. And the derivative of a square root, so you can write it over here if you like. You can also put it under the x squared. Is 1 over 2 times the square root of the same thing times the derivative of the inside, which is that right there, all over that denominator squared. So that just gets rid of the square root. Now, problem with this is it's a complex fraction, right? We don't like that. So we got to simplify it, but what we can do, we can cancel out these 2's first off, like this 2 and this 2 just cancel out. And then we get rid of a complex fraction like we've been doing.
Mr. Smith, are you talking to us?
Okay, had to pause there for a second. So what we need to do is multiply by that little denominator there, that's square root of x squared plus 1. Okay, but we're going to do it out here in the numerator and the denominator. So technically just multiplying by a big 1 over here, right? Like this is like in big parentheses. But remember what the quotient rule gives us. It gives us two things, right? Low d high minus high d low. So we're going to distribute this to here and here, and this just gets multiplied to there. So what we get when that happens is that when you multiply this square root to here, it doubles up with this square root right here. So that just becomes x squared plus 1. And that 2x is still sitting there. Minus, when you multiply it into this part, it cancels out this square root. That's the whole point of what we just did. So they go away completely. So all we're left with is an x squared times x, which is x cubed. Again, we got an x squared sitting here and an x sitting here, right? Because those 2's canceled out, if you think about it like that. All right. So that's all over. This is x squared plus 1 to the first power, and we're multiplying that by x squared plus 1 to the 1/2 power. So we are going to get x squared plus 1 to the 3/2 power. And that's going to boil all the way down. If you distribute the 2x, right here you get 2x cubed plus 2x. And then we're subtracting off an x cubed. So we get x cubed plus 2x over x squared plus 1 to the 3/2. So that's g prime, which we don't necessarily need right now because we're asking about, come back up here, the concavity. So we gotta get that second derivative. So what I'm gonna do is go over here to the side and derive it again. All right, we'll do that all in a different color just so a little bit easier to see. So g double prime is going to require the quotient rule as well. So it's low, which is x squared plus 1 to the 3/2 d high, which isn't hard, right? This is power rule. 3x squared plus 2 minus, then high, x cubed plus 2x times d low. So it's going to be the power rule happening there with that 3/2 coming down. So you're going to get 3/2. The inside stays the same. The new exponent's 1/2. Okay, let me get rid of this. Okay, and then we're multiplying that by the derivative of the inside. This is the chain rule happening, so it's 2x. That's the derivative of this x squared plus 1. That gets tacked on the end there. Okay? So that's what we got going on. And that's going to be all over the denominator squared. Now, when you square something to the 3/2 power, okay, let's do it down here. X squared plus 1 to the 3/2. When you square that, you multiply those exponents. So that just becomes 6/2 or 3 is what we really get. So it's x squared plus 1 cubed. Now, so as before, when you derive a fraction, so we just derive g prime, right? When the denominator has an exponent greater than 1, in this case 3/2, 1.5, what's going to happen is you're going to see that denominator, that x squared plus 1, in a few places. Actually, in 3 places specifically. You're going to see it in the low d high, right? There it is to the 3/2. You're going to see it in the high d low. There it is to the 1/2. And you're going to see it in the low squared. All right, now keep in mind, all we really have is this minus this. This is all multiplication in here, right? Over this. So what that means is we can cancel out. This just divides into this, but we can only cancel out the least amount of them, okay? So let's make up a little example here real quick without fractions. So let's say we had x cubed y minus x squared y squared. Let's put a number in here. I'm making this up as I go along just to show you another example without fractions, okay? And that was all over 3x to the 5th y to the 4th, okay? Because we got all these dumb x, y's here, we can cancel out some x's. You can see there's an x cubed here, there's an x squared here, and there's an x to the 5th in the bottom. So what that means is we can cancel out an x squared. What we're really doing there, okay, like I'd rather you not write it like this, is we're factoring an x squared and a y is what's happening from that top. That's going to leave us with 5x minus 4y up top there, okay? Hope that makes sense. So we got an x squared and a y, because you can take that away from the top. And in the bottom, we can take away an x squared and a y. It's not really factoring it out because it's all multiplication down there. So we're just pulling it off. And then we're going to have 3x cubed, y cubed. And these just cancel out right here. Okay, but if you look at that, all we're really doing, so rather than writing that all out, just look, you can cancel out the lowest exponent, right? So the x squared here is the lowest x exponent. So we can take away, again, that 3 is going to become a 1. Cool, we got the minus sign. The 4 is just chilling. The x squared goes away completely. And on the bottom, we cancel out 2 x's, so that's a 3x cubed. Then you look at the y's, okay? But you can only cancel them because everything has a y right now. So there's only y to the 1st right here. So we can cancel that out completely. The y squared becomes y to the 1st, and the y to the 4th becomes y cubed. All right? Now, to show you this too, just make sure we got this algebra going. If there was a plus something over here that didn't have x's or y's in it, like 1, now I can't cancel out anything because this divides into everything that's separated by a plus or minus. Okay, so that doesn't work out. But if that's not there, now we can. All right, so that's what's happening here, except we're doing it with an x squared plus 1, which is fine. It's all in parentheses, but the lowest exponent is at 1/2 power. So what happens is we're canceling out a 1/2 power. So this 3/2 right here becomes a 1. 3/2 take away a 1/2 is 1. So we get x squared plus 1 times 3x squared plus 2 minus x cubed plus 2x, right? That's all sitting there. And this x squared plus 1's gone. That's it. That's the lowest one. We take it away. So what's left here is a 3/2 and a 2x. So when you multiply that together, you get 3x. All over in the denominator, we canceled out x squared plus 1 to the 1/2. Well, there's a 3 here, so we got to take away a 1/2 from that. That's 5/2. And now all I got to do is simplify this thing. And maybe this seems like a lot, but the more you do this, like the easier it becomes, and you start seeing the same kind of pattern. So we're going to FOIL out this here. I'm going to do this right here. This is 3x to the 4th, cool, plus 2x squared plus 3x squared. That's plus 5x squared plus 2, minus 3x to the 4th, the negative distributes, minus 6x squared. So the whole top, 3x to the 4th cancel. 5x squared minus 6x squared is negative x squared, and then there's a 2. So the whole top just becomes this. Okay, we want to know where that's 0. We could factor this into root 1. I'm not going to factor it. If you get root 2 and negative root 2, right? So we want to know where this is 0. That happens when the top is 0, and that happens when x is plus or minus root 2. And we want to know where it's undefined. That happens when the denominator is 0, but that never happens. That has imaginary answers. Okay, so our whole second derivative number line only has negative root 2 and positive root 2 on it. And if you check those intervals, if you plug in a number less than, so negative root 2 is like negative 1.4. But even if you don't know that, plug in like negative 10. If you plug in negative 10, you're going to get a negative value out of there. Okay, because the top becomes negative over positive, right? If you plug in negative 10 into x squared, you get 2 minus 100. If you plug in 0, which is in this interval, you get 2 over 1. That's positive. And if you plug in something greater than 2, you get negative again. Cool, so that means, because it's the second derivative, g is concave down, concave up, concave down. So what we have, if we list this out, is our concave up interval is from negative root 2 to root 2. Our concave down interval is from negative infinity to negative root 2 union with root 2 to infinity. And because the concavity changes, and there's points there, we have inflection points, or points of inflection, the same thing, at negative root 2. We've got to find the y value, and positive root 2. We've got to find the y value. But remember, the function was x squared over the square root of x squared plus 1. Okay, that was g. So the y value, we find it by plugging in the g. So you plug in root 2 there, you get 2 over root 3 for both of these. Okay, not too shabby. All right, let's go back to these notes. And the next part says right here, it says, hey, go back to the warm-up. So that's this function right here, and do a complete analysis. What that really means is do all the stuff with the first derivative too. Okay, that's the increasing, decreasing, critical numbers, max and mins, right? Relative maxes and relative mins. So luckily, since we already did all the second derivative stuff, we have the first derivative chilling right here. All right, so let me switch back to blue so we're, color coordinated. We like that. And this just factors. So I'm doing this again for that second part that says do a complete analysis. A complete analysis is all the derivative stuff. So we did the second derivative stuff. We got to do the first derivative stuff already too. Or now. So luckily we're already there though. G double prime equals 0 when x is 0. Okay, that's coming from the numerator right here. It's factored, right? So x equals 0 comes from this. X squared plus 2 is never 0. And then g double prime is undefined, never, because the denominator is never 0, because it's x squared plus a number. So the only number on our g prime number line is 0. And if you plug a number into that, like -1, you get negative here, x is negative, -1 plus 2 is a positive, and then this thing over here is a positive. So if a negative times a positive over positive, that's negative, and that means on this number line we're decreasing. If you plug in something bigger than 0, you're going to get a positive, because these are all positives. And that means we are increasing. Okay? So adding to our second derivative stuff, which I wrote all the way down here, my sizing is a little crazy. But if you wanted a complete analysis of this, if I can shrink this down. Cool. Let me copy you. So a complete analysis of this would look like this. We'd have critical numbers at x equals 0. That comes from our first derivative being 0. Okay? We have an increasing interval from 0 to infinity. We have a decreasing interval from negative infinity to 0. We have a relative max nowhere, so none. That says it's decreasing and then increasing. That's what this curve does. So that's a min. We have a relative min at 0, and if you plug 0 into the original function, you get 0 back. Okay, so that's all the first derivative stuff, and then the second derivative stuff is right there. Cool, so this is our complete analysis, what we're calling that. Okay, and if you were to graph this function, you would see, look, all this stuff happens. So check it out. This is what this curve looks like. Here's negative root 2, here's root 2. Okay, I'm looking at my inflection points. Okay, that's right here. The y value is 2 root 3 and 2 root 3 for both, or 2 over root 3, right? So that says y value here. Doesn't really matter. Leading up to that point, we're concave down. So it kind of looks like this. It goes in like that. And after this point, we're concave down. So it looks like that. But in between them, we're concave up. But I also know that I'm decreasing until 0. So it goes like this, and then like this. So that's what that curve looks like. Okay, you can see concave down, concave up, concave down, and you can see decreasing here, and then increasing after. Okay, so we're gonna knock out these other ones here real quick. So we'll start with this. Cool, we'll do it down here. So f prime of x is 16x plus 2. All right, let's go ahead and find where that's 0. So this is relatively simple. This is just a parabola, right? By the way, we know it's a parabola. It's going to open upward, so we expect it to fit those features when we do all this work. If we make a number line for f prime at -1/8, we're going to find that it's negative on this side, positive on this side. So it's decreasing and then increasing. F double prime is just 16. Well, that means if you make an f double prime number line, like 16 is never 0. So it's just one big interval here. And if you check Any number, 16 is always positive, right? So that means we're concave up everywhere, which we expect because it's a parabola opening upward. So for this one, we have critical numbers. Oh, no parentheses there. At x equals -1/8. We have intervals increasing from -1/8 to infinity. We have intervals of decreasing from -infinity to -1/8. Cool. Which means, since it goes decreasing then increasing, right, down then up, like a parabola, like we expected, we have no relative maxes. We have a relative min at -1/8. And if you plug that into that function, so we got to find the y value. So we go all the way back to the original function. If you plug in -1/8 there, okay, do this with me. You're going to get -1/8 squared is 1/64. But times 8, that's an eighth. Plus 2 times -1/8, one's minus, is -1/4. Minus 15. But because we have eighths, 15, like over 1, if you multiply that 8, becomes 80 plus 40, that's 120. 120 over 8. Cool. And 1/4 is really 2 over 8. So that is -121/8. All right, that's all our first derivative stuff. And then second derivative is just concave up everywhere. So -infinity to infinity. Concave down. Never. And points of inflection. There's none because the concavity never changes. Cool. All right. This next one, not too bad either. So let's zoom in here. So this is a cubic. We expect it to go up, down, up because it has a leading positive coefficient, +1, right? So we expect it to be concave down, then concave up. And we expect it to be increasing, then decreasing, and then increasing again somewhere. So f prime of x is 3x squared minus 4. It's really 3x squared minus 12, but take the 3 out. Let me write that. I don't know why I'm skipping steps. It's 3x squared minus 12. We're going to take the 3 out. So that's going to be 0 at 2 and -2 because this factors. So if you make a number line for that, you're going to get -2 and 2. If you check those intervals, you're going to get plus, minus, plus. Okay? So that means we are increasing, decreasing, and then increasing, which is exactly what we thought our curve was going to do. Look up here. Increase, decrease, increase. Okay? The second derivative, I'm going to derive this version of it. We have 3 versions, right? We have that, we have this, we have this. Cool. I'm going to derive 3x squared minus 12 because it's easier for me, and that derives to 6x. So that equals 0 only when x is 0. So the only number going on our second derivative number line is 0. And if you check negative number, you get negative into the second derivative. Positive number, you get positive. So that means we're concave down and then concave up, much like we expected. Exactly like we expected. And if you list all this junk out, so we have critical numbers come from our first derivative. Remember, the function has to be defined, though. But that's just plus and minus 2. Okay? We have increasing from -infinity to -2 and decreasing from 2 to infinity. No, that's all increasing. Sorry, I'm trying to think ahead here. Decreasing between -2 and 2. We have a relative max at -2 because our first derivative is changing from positive to negative, right? Positive to negative. That means we go up then down. If you plug in -2 to this function, you get -8 plus 24. So that's 16. The relative min happens at +2 if you look at that number line. If you plug that in, you get -16. And then we have concave up is from 0 to infinity. Concave down is from -infinity to 0. And we have an inflection point. I switch back and forth between point inflection and inflection point. They're the same thing. At 0, and if you plug 0 into your function, you get back 0. So that's all that work right there. Nice and neat. Okay. Let's grab this next one. The next one's a little pain in the butt because it's got a square root. Where is it? It's hiding from me. There it is. All right, keep in mind when you see a square root, what's inside of that thing has to be positive. We're not going to take square root of a negative number. So where's what we just did? Right there. So we'll drop you right here. Blah. All right. So keep in mind again, x must be greater than or equal to negative 3. Because the inside of that square root has to be positive or 0. It can't be negative. All right? So that's going to limit our whole domain and everything when we start checking intervals. So when we derive this, we have to do the product rule. You get 1, right? That's the derivative of x times square root x plus 3 plus x times the derivative of square root of x plus 3, which is 1 over 2 times the same thing, times the derivative of the inside, which in this case is just a 1. Okay, so these 1s don't really need to be here, but they're there. So now we have a derivative that's a part fraction and a part not fraction. So the way you're always going to handle that is you're going to make it one big fraction. You get a common denominator. All right, so to get my common denominator, I need to multiply this by 2 root x plus 3 and 2 root x plus 3. Right? Like a big fraction we're multiplying by. Really multiplying by a 1. And make sure that goes all the way across. And when you multiply 2 root x plus 3 times root x plus 3, you get 2 x plus 3. Cool. Plus this other x, because now we have a common denominator, which is 2 root x plus 3. So f prime simplifies really nicely to, this is 2x plus 6 here, right? So it's going to be, yeah, so 3x plus 6 over 2 root x plus 3. Now, that's going to be 0 when x is negative 2. That comes from the numerator. That's going to be undefined when the denominator is 0. That's negative 3. But negative 3 is still a critical value because it makes the original function defined. It makes it 0. So our first derivative number line has negative 3 and negative 2. There's nothing back here, right? We can't plug in anything less than negative 3. That's imaginary stuff. If you plug a number in here, like negative 2.5, you're going to get a negative value. All right, because 3 times negative 2.5, think about that, is negative 7.5. Plus 6, that's still negative. Okay, if you plug in something greater than negative 2, like 0, you're going to get positive. So that means we are decreasing and then increasing. And then we got to find that second derivative. All right, so we'll come over here, f double prime is derive low, d high, which is a 3, minus high, d low, but think about that denominator. It's 2 root x plus 3, but that's just this to the 1/2 power, right? That's all we're doing. So you do a half times 2 and it goes away, and you get x plus 3 to the negative 1/2. Cool? That just puts this down the bottom like that. Okay, and that's all over the denominator squared. And when you square multiplication, 4 or 2 times a root, you square the 2, 4, square the root. X plus 3. And now we see we got this complex fraction, a lot like the warm-up, so we need to get rid of that by multiplying by the denominator we don't want. That's going to make this a whole lot nicer. That's a 3 there. Okay? So what that does here, when you distribute over here, it squares the root x plus 3. So we have 2 and a 3 make a 6. And then we have an x plus 3 there. Minus, when you multiply it to here, the root x plus 3's cancel. So you're left with minus 3x minus 6. That's the distribution of that negative. Okay? And we multiply on the bottom, you're going to get 4x plus 3 to the first times root x plus 3 is x plus 3 to the 3/2. Which means f double prime, so this is still f double prime. F double prime of x is, this is 6x plus 18, right? So minus 3x is 3x. Right? Let me mess this up. And 18 minus 6 is 12. Over 4 times x plus 3 to the 3/2. So we get the second derivative is 0 when x is negative 4. Okay, but that's outside of our domain, so we don't care about that. All right, and we get that the second derivative is undefined when x is negative 3. So we care about that. That works. Okay, so we make a second derivative number line, which just has negative 3 on it. There's nothing back here. And if you check a number greater than negative 3 into your second derivative, you're going to get positive, which means we are concave up. Okay? So what that does, I'm going to zoom in a little bit here. If we list all of our junk out, I'll do it over here. From our first derivative number line, we have critical numbers at x equals negative 3 and x equals negative 2. Okay, they both count because they make the function defined, f defined, but they make f prime undefined and 0. Negative 2 makes it 0. So we have increasing from negative 2 to infinity. We have decreasing between negative 3 and negative 2, and that means we have a relative min there. So we have no maxes. We have a relative min at negative 2 comma, you got to plug it back into our function, which was this thing. If you plug negative 2 into here, you get negative 2 times 1. So that's negative 2. Cool. And then we have concave up from negative 3 to infinity. Concave down, never. And points of inflection, there are none because it never changes concavity. All right. So it's number 3. Woohoo! Let's keep going. Let's go all the way back up here. All right, we gotta do this fourth one. What time is it? We got time. Yeah. Give me this function. Boom. So I know sometimes you see like e to the x's and you don't like those, but they're not too bad. I'm gonna try and keep this all the same size here rather than zooming out. Let's see if I can do it. Shrink you up. Oh, not like that. Yeah, okay. No. Okay. We'll try this again. Oh my gosh. Oh, now move you. No, it's, oh god. Okay. The touch screen is failing me here. Yeah, move you. No. There we go. Just move over here. Good God. Okay. Whew. Laugh at my struggles. So, the domain of this is all real numbers because you just have an x and e to the x. They're never undefined. F prime by the product rule is e to the x plus x e to the x. So, yeah, you see these e to the x's, and maybe that makes you feel a little uncomfortable. I don't really know. But they actually end up working out really nicely. You get that. And that's only ever 0. It's never undefined. It's only 0 at negative 1. E to the x is never 0. Okay? We factor because we look at each factor, right? E to the x, never 0. 1 plus x, 0 at negative 1. So our f prime number line just has negative 1 on it. And if you plug a number in less than negative 1, like negative 3, e to the negative 3 is a positive value. Doesn't matter if the exponent's negative. E to a power is positive. And if you plug negative 3 into 1 plus, so you're going to get a positive times a negative is what happens there. That's a negative value. So we're decreasing here. And if you plug in something bigger than 1, you get positive. So we're increasing there. Okay? And then the second derivative, I would just derive this version of it right here. Cool. You're going to get e to the x. Plus, we got to do the product rule in that second part. So that becomes e to the x plus x e to the x. So the second derivative, if you take an e to the x out and simplify that, is 2 plus x in there. Okay, like this here is just 2e to the x. Algebra kids. All right, so our number line for f double prime, so the only thing that comes off of that is negative 2. So our number line for f double prime is negative 2, and by the same reasoning, you plug in something less than negative 2, you get negative and then positive, but because this is our second derivative number line, that tells us that. And then we know all this junk. So we know critical numbers are at x equals negative 1. We don't need to write the point. Just x equals negative 1. We're increasing from negative 1 to infinity. We're decreasing from negative infinity to negative 1. We have a relative max nowhere. And we have a relative min. My max and min look very similar. Relative min is at negative 1. If you plug negative 1 back into our function, which was x e to the x, you get negative 1 e to the negative 1. Well, that's negative 1 over e. That's what those exponents do. Cool. And f double prime tells us we are concave up from negative 2 to infinity. We are concave down from negative infinity to negative 2. And we have a point of inflection at negative 2. And same thing, if you plug in negative 2, you're going to get negative 2 e to the negative 2. But that's just negative 2 over e squared. Okay. So that wasn't too bad. All right. And last one, let's go all the way back up. Okay. Go all the way back down. So let's shrink you up. Zoom in. All right. So this is the first derivative. Is 2/3, and then you're going to get to the negative 1/3. So just put that right down the bottom. That's going to be x squared minus 4. Why is it not filling in there? To the negative 1/3. That puts it down the bottom, so it's positive 1/3 times the derivative of the inside, which is 2x. So f prime is really 4x over 3x squared minus 4 to the 1/3. Cool. So we get that f prime is 0 when x is 0. And we get that f prime is undefined when x is plus or minus 2. Cool. Now those are all critical values because all three of those, 0, 2, and negative 2, make this function defined. All right. And when we make our number line, we put negative 2, we put 0, we put 2. Right, this is f prime out here, right? Make sure you know you're testing f prime. If you plug values into that, if you plug a negative number in, like negative 4, right down in here, you're going to get negative on top over, but negative 4 squared is 16, and 16 minus 4 is 12. That's all positive stuff in there. So a negative over a positive. So that means this is negative, which means my function is decreasing. If you plug a number in after negative 2, but before 0, like negative 1, right in here, all right? You're going to get negative 4 over, if you put negative 1 into here, you get 1 minus 4, which is negative 3. Okay? And this is the cubed root. That's what this means. The cubed root of negative 3 is a negative number. So a negative number times 3 is negative. So this is really positive here. If you plug in 1, similarly, you get positive over negative, which means we're decreasing. And plug in something big positive, you get positive again. You get everything's positive like that. Okay. Then we need our second derivative. So f double prime of x is low 3 x squared minus 4 to the 1/3 times d high, that's just 4, minus high 4x times derive low. But when you multiply 1/3, so you're doing the power rule on the bottom here, right? You get 1/3 times 3, that's a 1. Then you get that to the negative 2/3. So that puts this on the bottom right here. To the negative 2/3. And then you get times the derivative of the inside, which is 2x. And that's all over the denominator squared, which gives us a 9. That's this. And squaring this to the 1/3 makes it to the 2/3. So we have 9 x squared minus 4 to the 2/3 like that. Okay? Now we got a complex fraction again, so you're like, oh man, but we do the same thing. It's really not too bad. It simplifies everything out for us. We got to multiply this by x squared minus 4 to the 2/3. Like that. So again, distribute here and here. When you do this to here, x squared minus 4 to the 2/3 times x squared minus 4 to the 1/3 becomes x squared minus 4 to the 3/3. Well, that's just the first power. So the 3 and the 4 make a 12. And then you just have x squared minus 4. So that worked out nicely. Minus, when you multiply to here, it just cancels out the bottom, that denominator. So we're left with 4x and 2x, which is 8x squared. Over, when you multiply it to here, that becomes to the 4/3 power. Like that. Okay, and then the whole thing, if you distribute that 12, f double prime of x becomes 12x squared minus 8x squared is 4x squared minus 48 over all this junk. Cool. And if we take a 4 out, we get x squared minus 12 in there. Okay, so this factors into 4, x minus square root 12, x plus square root 12. There we go. So our second derivative number line, I'm starting to zoom out, which I didn't want to do, is going to have a bunch of numbers on it. So you can look wherever that makes it 0, but it's going to be negative root 12 and then negative 2. We know negative root 12 is less than negative 2. Okay? Root 12 is bigger than 3 because root 9 is 3. Okay? Then we're going to have positive 2 and then positive root 12. We got to check all these intervals. But look, I'm going to check this factored version kind of thing over here. And keep in mind, to the 4/3 power means raised to the 4th and then cubed root. Well, if you raise anything to the 4th, you're going to get a positive value back. So this denominator is always positive because I'm raising it to the 4th power. So if I plug in something less than negative 12, like negative root 12, plug in like negative 20. This is negative and this is negative, which makes a positive, right? Negative times a negative is a positive. So you have positive over positive, which is positive, which means we are concave up. If you plug in something in here, like negative 3, okay? Negative 3 minus root 12 is negative, but negative root 3 plus root 12 is positive. Cool, so that gives me a negative, and the denominator is still positive because it's to the 4th power. Negative, concave down. If you plug in 0, the same thing happens. You get negative over a positive. That's negative, concave down. If you plug in 3, the same thing happens. You get negative over positive. That's concave down. If you plug in something greater than root 12, you get all positives up top. So you get this. There you go. So our number lines tell us all this stuff. We have critical numbers at x equals 0 and plus and minus 2. We have increasing from negative 2 to 0, union 2 to infinity. We have decreasing from negative infinity to negative 2, union with 0 to 2. Which means we have a relative max. Got away from me there. Max. So this goes down, up, down, up. So relative max at 0. You can see that happening. 0, comma. If you put 0 into this function here, you get negative 4 to the 2/3. That's the cubed root of 16. Okay? You can reduce that, but we'll leave it as cubed root of 16. Relative mins happen at negative 2. If you plug in negative 2, you get 0 and 2. Plug that in, you get 0. Okay, and then for concavity, we have concave up from negative infinity to negative root 12, unioned with root 12 to infinity. We have concave down from negative root 12 to negative 2, union with, we got to break apart these intervals because they're separate, even though they're right next to each other, negative 2 to 2, union with 2 to root 12. And that means we have points of inflection at negative root 12, which we're going to find the y value for that, and root 12. Remember, the sign has to change for it to be a point of inflection. So negative 2 and 2 are not points of inflection. And because our function was something I forgot already, x squared minus 4, if you plug in that, you get 12 minus 4 to the 2/3. But that's 8. So that's the cubed root. Oh, man. Got all the way to the end. My computer's freezing for a second. Hang on. Hope it's for a second. If I lose this whole video, it's just not getting done. Uh-oh. Okay, let's see if I can finish this. Well, if you plug in, you're going to get cubed root of 8 is 2 and squared is 4. So these are both 4s if it doesn't let me write it. Here we go. I did too much. All right, you get 4s. Okay, too much. Too much for my poor little computer.